Zhichen Zhang from Tianjin University. Welcome to our SmartMat academic seminar. Today, Professor Javier Perez Ramirez from the ETH Zurich will give us a presentation. Now, I'd like to briefly introduce Professor Perez Ramirez first. Javier Perez Ramirez is since 2010 a full professor of Catalysis engineering at ETH Zurich. His research pursues the nanoscale design of catalytic materials, enabling the transition towards sustainable chemical and energy production. He studied chemical engineering at the University of Alicante and received his PhD at Delft University of Technology in 2002. Javier is a highly cited researcher in the field of chemistry and has been recognized by several awards, most recently the EFCTS Robert K. Gracelli Award for Catalysis in 2021 and the 2022 Environment, Sustainability and Energy Horizon Prize from the Royal Society of Chemistry in 2022. He serves as a chair of the editorial board of Green Chemistry and directs NCCR Catalysis, a Swiss center of competence in research devoted to developing carbon-neutral chemicals across the whole value chain through catalytic processes. He has published over 550 articles. Current H index is 121, very high. Today, Professor Perez Ramirez will give a talk about catalysis and sustainability, a journey from atom to planet. Let's welcome Professor, please. Thank you.
Do you see my screen and see me well?
Yeah, no problem, please.
Okay, thank you very much, Titan, for the very kind introduction, and thank you to SmartMat and Tianjin University for inviting me to give this seminar. I'm going to discuss catalysis and sustainability covering multiple scales from atom to planet. And I think to start, it's important that we define what the scales we are talking about. You have seen a picture of molecules, and we have a catalyst particle, a reactor now, a chemical plant, the supply chain where chemical plants are placed, and ultimately the planet. And it is very important to understand that in catalysis, we cover all these scales, and the decisions that we take for the atomic level design of catalysts have huge implications for our planet, and particularly for improving the sustainability of operations towards chemistry and energy in our planet. So once I have defined what scales we're talking about, I will try to give you some glimpse of research in the area of catalysis that spans all these scales, from atoms to planet. To start, I think I have to say something about the little circularity that we have in our economy. Circularity is a necessary condition to achieve sustainability. And currently, let me just put my laser pointer. Currently, we extract a huge amount of materials, what we call natural capital, and this material goes through society only once, mostly. So only 7% of the materials that we take from natural capital are recycled. That means our society has a very little degree of circularity. About 7% of the materials are used more than once. And of course, this is one key aspect that we have to improve towards sustainability. Circular economy requires that we are able to reuse and recycle products. The other aspect, which is very important, where catalysis plays a role, is actually that if we see most of the chemicals that we manufacture and we do an analysis of sustainability under the lenses of planetary boundaries are boundaries that our planet cannot exceed in order to achieve sustainable development. We realize that if we do this analysis over 500 chemicals covering small molecules, but also polymers and more functionalized molecules, we see that more than 99% exceed at least one planetary boundary. Most of the time is the climate change boundary. That means that all chemicals we make, or almost all chemicals we make, are under this definition unsustainable. And that is because of the fossil nature of the feedstocks that we use to make these chemicals. So improving circularity and having renewable feedstocks is a very important aspect towards reaching sustainable development. And this is where catalysis can have a say in improving the situation. I would like to start with an example of a step towards circular economy. And this is an announcement made by Covestro a couple of years ago on the new chlorine production facility called Deacon 2 in Shanghai. Essentially, what this facility does, it's in relation to the production of polyurethanes. Polyurethanes are very important polymers, and the demand for these polymers greatly increases with time. What happens in polyurethane production is that we start with chlorine and carbon monoxide, and after 3 steps, we end up with the polyurethane. But in the second step, which is the synthesis of the diisocyanate, we produce a huge amount of hydrochloric acid. About 4 moles of hydrochloric acid per mole of diisocyanate. This hydrochloric acid has been traditionally neutralized rather than recycled. And of course, neutralization leads to huge cost, but actually it reflects the linearity of our society. We don't reuse this chlorine effectively. Instead, we just neutralize it to produce salt. So what happens in this plant is actually that you can recycle that hydrochloric acid by oxidation into chlorine, which is the feedstock for making phosgene to produce the diisocyanate. Developing catalysts for oxidizing hydrochloric acid to chlorine has been extremely challenging, and only very recently scientists have succeeded in making this. We have worked on this development together with Covestro for many, many years, basically since 2005 until 2012, so 7 years of work. And I'd like to give you a glimpse of how this plant for chlorine recycling looks like. In this process for chlorine looping, it's conducted in fixed bed reactors. You can see the fixed bed reactors over here within the polyurethane facility, where we have 2 catalytic materials. I'm going to focus on the top one for the video for simplicity. It's the primary catalytic material. And if we penetrate in the catalytic material, you are in the micron range, where you see in orange the support, in blue you have the active phase, and in green you have the binder to make particles. And if you go to the atomic scale, you see the catalytic surface that splits oxygen, cleaves HCl bond, OH groups recombine to produce water, and chlorine groups produce chlorine, recovering effectively chlorine. Now, this catalytic material is based on a ruthenium oxide catalyst epitaxially grown on tin oxide as carrier. And this epitaxial growth, where you see two layers of ruthenium oxide, has been essential to have a very stable catalytic material displaying a high activity and also trying to economize the utilization of a very expensive noble metal like ruthenium oxide. So effectively, the optimal catalyst that is implemented in industry contains two layers of ruthenium oxide epitaxially grown on tin oxide. Both ruthenium oxide and tin oxide possess the rutile structure, rendering this film type architecture for the ruthenium oxide, which makes a very high dispersion of the active phase, and most important, a very high stability because of the lattice matching between the active phase and the support. Now, seeing is believing, as you know, so this is a high resolution transmission electron micrograph of the catalytic material, where you can see two layers of ruthenium oxide epitaxially grown in a film-like architecture on tin oxide. So this is a catalytic material that was developed rationally in order to achieve circularity regarding the chlorine looping in the production of polyurethanes. That's how catalysis can help. Another example that I would like to share with you relates to the conversion of carbon dioxide, which is a renewable feedstock, into green methanol using hydrogenation of carbon dioxide. And also, to start this case study, I would like to show this announcement from Total Energies, a French energy firm, together with Sunfire, which is the manufacturer of hydrogen water electrolyzers to green hydrogen, that have announced the go-ahead for installing a green methanol plant in Germany, in Leuna. And I would like to show you a little bit the development of catalytic technology for this particular application, which we undertook in my group for many years as well in collaboration with Total. Please keep in mind that this announcement is also very recent, 2021. The catalyst for hydrogenating CO2 to methanol that we discovered and developed in my group is based on indium oxide. This catalyst was discovered in 2015, patented in 2015, and published in 2016. And it relates to the fact that in order to do CO2 hydrogenation, we are using a reducible oxide where we can create oxygen vacancies in the material under reducing conditions of the reaction and at moderate temperatures in order for the reaction to take place. In these vacancies, what happens is that CO2 and hydrogen activate. So you have seen the heterolytic splitting of hydrogen on the vacancy, forming protons on the oxygen and hydrides on the indium atom, and the CO2 activates also in the vacancy. And what happens next around this vacancy, very well discretized vacancy, is that there are addition of 3 moles of hydrogen to the CO2 moiety that goes through different intermediates until you form in a very selective manner methanol and water. And this is by far the most selective catalyst that exists today at reasonable levels of CO2 conversion to hydrogenate CO2 to methanol and not producing CO as product of the reverse water-gas shift reaction. This is, of course, a model catalyst, and that the discovery was done actually with what we call research catalyst. And a huge effort costing us many years went from this fundamental catalyst to a catalyst in technical shape that can be applied in industrial reactors. And you see here the extrudates of the indium oxide-based catalyst. in addition to indium oxide base, which is indium oxide, which is the primary active phase, it's very important to have the right carrier, and in this case is monoclinic zirconia. And you can see here that we also have palladium in the catalytic material. Palladium is essential in order to boost the activity of the catalyst by improving the splitting of hydrogen, which is actually the rate limiting step of the reaction over the indium oxide. So the architecture of that catalyst that was in that bottle could be different. And you can see here two different architectures, one prepared by flame spray pyrolysis on the left, on the right, prepared by simple impregnation. These two architectures actually render an equally effective material, displaying a space-time yield of about 1.3 grams of methanol per hour per gram of catalyst, which is actually very high. The material in technical form contains 5% of indium oxide and a small amount, 0.75 palladium. Now, what is very important in these architectures to deliver the function of producing methanol in a very efficient manner is that you need to combine acid-base function, which is delivered by the indium oxide, with the ability of doing the redox chemistry, which is the hydrogen splitting. And this is done by either palladium single atoms in this architecture that are stabilized on the surface of indium oxide, or it can also be done by indium-palladium alloys, which can be produced by impregnation, as long as the acid-base function, which is indium oxide, and the hydrogen splitting function are integrated close together in the catalytic material. So that shows you how important is the nanostructure of the material. Without atomic control, solving planetary problems is quite difficult. Now, this graph shows you that actually if you shift from fossil methanol to green methanol, actually you are improving a lot the sustainability of the process, which is very poor in fossil methanol because of the use of fossil natural gas to produce syngas. And if we shift to CO2 and green hydrogen, actually, there is no red traffic light anymore. Instead, what we create is Earth system credits because we are removing CO2 from the air to produce methanol. So the environmental effect of producing green methanol is very positive. But sometimes what happens with the environmental benefits, which is illustrated here by the E in green, actually goes against the red E. And the red E, what illustrates is economy. So very often green technologies are much more expensive than fossil technologies because they are much less optimized, because they are much newer, for example. However, I want to show you here a case study that was published in Green Chemistry in 2023, analyzing the situation for Europe. And this is the situation for Europe only. So it's very important to highlight. This is the cost of methanol in 2019, December 2019, and the cost of ammonia also in 2019. And you can see that the green methanol or green ammonia are significantly more expensive than fossil methanol and fossil ammonia. And so this is what I was reflecting by the red E. There are clear benefits of moving to green technologies, but who pays this huge price difference between green and fossil products, right? But what happens is that, you know, in Europe, particularly, we are suffering a lot from the energy crisis associated, among others, by the conflict between Russia and Ukraine. So the cost of natural gas has increased significantly. And because of that, fossil methanol and fossil ammonia have become much more expensive. And so if we now analyze the cost of green versus fossil, let's say methanol, what you see is that in July 2022, green methanol and fossil methanol have a very similar price and was even lower in April 2022 when it was done green. So socio-political and geopolitical situations could actually give a huge boost for implementation of green technologies. And you can see the effect even more pronounced for ammonia. Green ammonia in Europe, if the supply chains will be available, will be much cheaper compared to fossil ammonia. Now, I've shown you a very mature example of converting a renewable feedstock like CO2 into green methanol, right? And this is mature. It has costed us many years of work, luckily, we're very fortunate that this process is now implemented in industry. But in research, we also have to develop new systems and find new discoveries, right? And this is something that is less mature, but very exciting for us. And we have been looking into electrocatalytic ways to valorize carbon dioxide into long-chain hydrocarbons. And this is a recent publication from like 2 years ago in Nature Catalysis, where we were looking at alternatives to copper for producing long-chain hydrocarbons via CO2 electroreduction. Copper is the most extensively studied electrocatalyst because it's claimed to be the one that produces more multi-carbon products. Up to 16 carbon products is produced, right? They produced. And we, decided to look into nickel. But not just metallic nickel, right? Because metallic nickel is actually a pretty terrible catalyst for CO2 reduction. It will mostly reduce water into hydrogen due to a very strong adsorption of carbon monoxide on the surface of metallic nickel. Instead, we have been working with polarized nickel catalyst, which is trying to incorporate oxygen on the surface of the catalyst in a stable manner. And we have achieved that by using, for example, nickel phosphate as precursor of the catalyst for producing, for converting CO2 electrochemically. What we have discovered in this publication is that polarized nickel sites, that is positively charged nickel associated with the presence of oxygen on the catalyst, could reduce CO2 into long-chain hydrocarbons exceeding the carbon number of classical copper catalysts, which essentially stop at C3, and we are able to make, with nickel, polarized nickel, up to 6 carbons in the molecule in one step. Not only that, we are much more promiscuous in the product distribution. Instead of 16 products, we have been able to make 29 products. That means there is new chemistry beyond copper for electrocatalytic reduction of CO2. The reason for this we attribute to the fact that when you have nickel phosphate compared to metallic nickel, you always have a signal of polarized nickel, which stays upon use of the catalyst. So this catalyst is very stable. You can see here the Faraday efficiency to C2 to C6 hydrocarbons, right? And this nickel 2 plus is actually responsible for the coupling ability of this catalyst, which follows a ASF distribution typical of Fischer-Tropsch with C1, C2, C3, C4, C5, up to C6 products. And the idea behind the coupling ability of polarized nickel is that upon polarization, actually, compared to metallic nickel, illustrated here by the nickel foil, there is a shift of the binding energy of CO to weaker values. And the weakening of the CO2 absorption, of the CO absorption, makes it possible for fragments to desorb and also provides the catalyst with ability to couple the CO into long-chain hydrocarbons. You can see that the Faraday efficiency is at about 12%. So there is a long way to go. There is a long way to go. That's why I was stressing that these are kind of discoveries, low maturity projects, but they clearly reveal that you could do very new chemistry with alternative catalysts rather than just looking into the same copper. Keep looking into copper. I think there is life beyond copper in CO2 reduction, and this study demonstrates that. Other aspect which is very important in catalysis, or where catalysis could be very important, is on solving the huge problem that we have on plastic waste and heterogeneous catalysts to do the chemical recycling of plastic waste. It's a very interesting area of research. And I want to show you here one example that we have published very recently in Angewandte Chemie, where we have used very tiny nanoparticles of ruthenium supported on titanium oxide to convert high-density polyethylene with a very high molecular weight. This is consumer-grade polyethylene caps, actually, to convert it into liquid products. And so using hydrogenolysis chemistry. And so here it's just to show you that actually you could make a pretty interesting products out of waste plastic, tuning the nanostructure of catalyst, in this case, ruthenium nanoparticles. And what this graph compares is actually that if you compare pure polyethylene with exactly real polyethylene, so real caps from Coca-Cola bottles, actually the product distributions that you will get are very different. We get less gas, we get probably a similar yield of fuel and oil fractions and more solids. And that's because of all the additives that exist in real plastics, which will need to be taken into account into the design of catalysts, because pure plastics are actually a nice way to start research, but not representative, because every plastic has multiple additives which will play a role in the catalytic function. Okay, so I have shown you until now the importance of nanostructure of the catalyst in order to transform very challenging feedstocks, to improve the recyclability, to improve the circularity, and to improve the renewability of catalytic conversions. I hope you are convinced by that. And now I would like to switch for the second part of my talk. Let me see, to another area. And, you know, my job description, and I think for many that do catalysis, this is our job description, is to understand the relationships between the structure of the catalyst, what property this catalyst has, and what performance it delivers. So the performance has to be maximal. You want to be here. You don't want to be here, or you don't want to be here. So you need to understand what structure could create the catalyst that delivers this performance. For that, you need to synthesize the right active site. And the right active site, which is here, the star that is the brightest in the sky, delivers a certain property that we normally will gather through a spectroscopy or other characterization techniques. So that's all what we're trying to do in catalysis, uncovering the mysteries and relationships between how to synthesize the catalyst that has the right structure, that delivers maximized performance, and understanding what property makes that catalyst delivering that optimized performance. That means, what is the descriptor of my catalytic conversion? And so I want to illustrate this because in heterogeneous catalysis, very often we create these kind of architectures where Typically you can see here nanoparticles. These are supported nanoparticles. This is a gold nanoparticle. This is an example I took from this publication in 2009. But if you look more carefully with a microscope, you can see that in addition to these beautiful and bright gold nanoparticles, the catalyst also contains some dirt. And this dirt, I'm going to just describe it as dirt, excuse me for the word, actually comprises some kind of gold clusters. You can see here like what it looks like a cluster. You can see also some degree of clustering around here. And even some of this gold is stabilizes atoms. These are stabilized single atoms. So that is what I'm going to shift now until the end of the presentation. I'm going to look at what can we do with these atoms that we can hardly see in micrographs. And the reason of working with single atoms and to exploit single atoms is because they achieve, in a way, of maximize dispersion. It's the best way to disperse metal because in a nanoparticle, as you know, only surface sites will be accessible by reactants. And so we are actually underutilizing quite a lot of the metal very often. So how can we make catalytic materials that only contain atoms? How can we use these atoms to carry out unique reactions with a unique reactivity in a sustainable manner? So the structure of a typical single atom is illustrated here. I used here this slide to introduce what single atom catalysis is. And single atom catalysis is essentially heterogeneous. Catalysis is essentially a metal atom that is stabilized in a solid scaffold, in a solid carrier, sometimes called host, in a coordination site of the host so that the metal atom is stable. As you can see in this real-time microscopy sequence where you could see that that single atom, in this case, I think is palladium, is stable in the cavity of this host, of this carrier. And this particular carrier in this slide is carbon nitride, graphitic carbon nitride. One postdoc of mine, now professor in China at the Nanjing Forestry University, Pen Chen, has been working in my lab extensively on these catalytic materials, and these are some of his publications. Hopefully he's in the audience today, and so he could enjoy what he did through this slide. Now, how does a uniform single atom catalyst look like, right? Because that's the point, right? We don't want to make nanoparticles and we don't want to make clusters. And this is what it looks like. So this is a micrograph of a single atom heterogeneous catalyst comprising platinum atoms on activated carbon. And we are using these materials extensively for multiple reactions. And I want to show you one reaction which is very important, particularly in China. And this is the production of vinyl chloride via acetylene hydrochlorination. Platinum single atoms stabilized on carbon are extremely stable materials for hydrochlorinating acetylene into VCM or vinyl chloride monomer. And that's a technology that is very important to replace mercury catalysts that are used today to produce this PVC precursor. And I want to show you this because that's the reaction I'm referring to. So acetylene hydrochlorination to vinyl chloride monomer. And you see here the carbon structure. And this is the cavity and the oxygen atoms on the carbon where the platinum single atom is stabilized. And you can see that the platinum single atom has some chlorine, and it has some chlorine because it's prepared typically from chloroplatinic acid. And this material catalyzes very effectively the reaction between acetylene and hydrochloric acid. And the reaction actually proceeds like this. So these are the different elements of the reacting system that I'm going to describe. And you can see what happens, right? Hydrochloric acid activates on the platinum atom and delivers the chlorinating further the single atom. And the hydrogen actually goes to the oxygen functionality. And acetylene is never absorbed on the single atom. It's absorbed on the neighboring side of the carrier, of the support. And so then that is producing the coupling. So basically the transfer of the chlorine from the platinum single atom to the acetylene moiety that is absorbed on the carbon. The reason why I show you this is to you is because it clearly shows that the platinum atom doesn't do the whole job on its own. It requires the host to activate the triple bond. And very often it is conceived that the single atom is doing the whole job, but in single atom catalysis, the carrier is not just the stabilizer of the single atom. Very often it has a co-catalytic role, and therefore it has to be designed accordingly. In this case, the catalytic role is adsorption of acetylene. The platinum single atoms for acetylene hydrochlorination were reported in 2020 in Nature Catalysis. And what I want to emphasize again is that when you design a single atom catalyst, you have to take care not only of the metal atom and its environment, but also on the structure of the carrier material. Because the carrier material is not just a carrier, it has a catalytic function most of the times. Now, making single atom catalyst is not easy. And the first paper that was coining this term, single atom catalysis, published by Chan Tao and Jun Li in Nature Chemistry back in 2011, said it very clearly, right? They say that making this single atom catalyst that they use for CO oxidation is very challenging. And in order to make them in isolated form, so that there is no clustering of the metals, they had to control the platinum loading to very low values, so that there would be no clustering, essentially 0.17 weight percent. So I have here two comments. We would like to have single atom catalysts with higher loadings without agglomeration. And we would like to use single atom catalysts for more complicated reactions, more high added value reactions than just CO oxidation, right? So progress in this direction has been done, and I would like to share that progress with you. The reason why we want to make single atoms with larger loadings is because we want to increase the number of active sites per gram of catalyst. And one way to do that is increasing the metal atom density. And the metal atom density, of course, is the metal loading. If you increase the metal loading, you actually increase the reaction rate. And if you increase the reaction rate, you decrease the volume of catalyst that you need in a reactor in order to achieve a certain conversion. But of course, as I told you before, if you put large amounts of metal, and large means at this point more than 1% of metal, what happens very often is that these metal atoms are not well anchored on the carrier. They will then be mobile, and upon moving, they will form nanoparticles. And then you form clusters of nanoparticles. And therefore, basically, the purpose of the exercise is defeated, because what you want is to increase the density of single atoms. You don't want to make clusters. So we have worked extensively on approaches to make sure that we increase the metal atom density, but the metal atoms are stable. And I have here an example of one process to prepare what we call ultra high density single atom catalyst. For that, we are using a two-step method, and two-step annealing method. That's how we call it. We developed this together with Luchon in National University of Singapore back in 2022. This method is widely acclaimed. Many people are using this method these days, so we are very happy about that. Let me show you how this method works. You have here a carrier. This is a nitrogen doped carbon. And you see here the hydrogen functionalities connected to the nitrogen. And this is actually the place where you could stabilize the single atom by creating a bond between the metal atom and the nitrogen, basically replacing hydrogen by your metal. And that's what we call the coordination site. This is the place where you can anchor the metal. So the first thing we do is actually we put a lot of metal because we want to increase the metal content, right? So we put a lot of metal, and I illustrated this with nickel chloride. So this is nickel in dark green, and in lighter green is chloride. So that's a nickel precursor. You can see here the exact spectra of the deposit catalyst, where we only see bonding between nickel and the chlorine in the nickel chloride. So we put much more metal than coordination sites we have. That's the first step. Then the second thing we do is a first step low temperature annealing. In this low temperature annealing, what we basically do is to remove some of the chlorine ligands from the nickel chloride. And upon removing some of the chlorine ligands, the nickel side will go and attach to the nitrogen functionalities on the host. And you can see the catalyst at this stage contains still chlorine because there is still some chlorine, and this guy has chlorine, but you also see the bonding of the nickel atom to the carrier, nickel-nitrogen bonds. Now, if you will now use this catalyst right now or calcine it at high temperature, you will be in trouble. You will be in trouble because this nickel is mobile. This nickel is anchored, but this nickel is mobile. So that mobile nickel will sinter with other nickel, producing nickel nanoparticles, which is the unwanted process by which most of the times when you prepare high-loading single atom catalyst, you normally get nanoparticles. So, and that's the two-step name in the synthesis method makes sense. What we do after this selective anchoring is we do a metal removal where we remove by simple washing in water the excess of precursor that has not been anchored because there are not sufficient anchoring sites. And upon now removing this metal that was in excess, it's no problem whatsoever to do a high temperature calcination to remove all the chlorine from the nickel, forming only nickel-nitrogen bonding because that nickel was already anchored. So that's a little bit how the system works. That's why it's two-step. This is the first annealing step and the second annealing or high temperature treatment step. And in between, you have to remove the excess metal that you can, of course, recycle for an upcoming preparation. Doing this, we have been able to, for 15 metals, you can see all the metals here, 5 supports. I'm showing you here 3, ceria, nitrogen doped carbon, and polymeric carbon nitride. Prepare materials with up to 23% metal content in single atom form with single atom dispersion. And very important, this has been prepared even in kilo scale because that's a very important aspect of our synthesis method. This is scalable. Many of the catalysts that we have prepared, you can see here for PCN, for instance, we can make 22, 23%. rhodium or platinum or 20% iridium, you can see carbon-based carriers they have many more coordination sites, so they can accommodate much larger metal contents compared to inorganic carriers. Inorganic carriers like Syria at best could accommodate a significant amount of, let's say, palladium, I think is this one here, about 8 or 9 weight percent. But if you move to carbon-based materials, you could see that systematically you increase the loading because of the availability of coordination sites. It's much easier to make them. It will be a breakthrough to prepare a single atom-based catalyst on an organic and on an inorganic support, like an oxide, with contents of 25 weight percent. And actually, many groups are working on that, how to increase the binding sites on oxides, including our group. So we hope to make progress on that. But making ultra high density catalyst, it's about tailoring the carrier. And that's what you have to do, because you need to produce a carrier that has this huge amount of binding sites that can be occupied by the metal precursor. Okay, so all these materials we have prepared in a standardized way. So this is the robot we have used to prepare the ultra high density catalyst, right? So every catalyst is prepared in the same way by a robot. It means it's in a standardized way of preparing materials. You don't need to worry about the reproducibility, because a machine does it for you. It's not that you have a better student that has better hands than the other student. This is a recipe that is run by a robot, and the robot works every day and everywhere in the same way. It's very important in catalysis. We need to deliver a standardized method for catalyst preparation so that everyone can reproduce their data. A very important aspect in which we are working, this is a recent publication, is in using, and that relates also to standardization, is in using language models for accelerating synthesis planning in heterogeneous catalysis. That means being able to read protocols from papers and understand how they could be better standardized to accelerate discoveries. Very often what we see is that machine learning algorithms and language models are not very accurate in reading, in text mining. That's what we call text mining, because protocols in the literature are not standardized. They are not written in a standardized way. So in this paper published in Nature Communications in December last year, what we propose is, on the basis of the outcome of the model results, is how the community could write synthesis methods for example, for single atom catalyst synthesis, so that machine learning models can read them much more effectively, so that we do not actually need to read papers, but an algorithm can read papers for us and do a first filtering of information, so that we can plan what to do, what has not been done yet in a certain area of research in catalysis. So normalization is important for the synthesis, but normalization and standardization is also very important as to how we report synthesis methods. And not only that, standardization is also important because of the relevance of characterizing catalyst in general, and single atom catalyst in particular. So the technique that we often use for characterizing single atom catalyst is transmission electron microscopy, because transmission electron microscopy gives you a very quick image about confirming the atomic dispersion of your metal. You can see here 1% platinum single atom catalyst stabilized on nitrogen doped carbon. And that's a pre-processed image. This is an aberration corrected scanning transmission electron micrograph. Now, the point is that if now I have a robot to prepare hundreds of samples, even in one day, how can I standardize the characterization of those samples that I would need to confirm whether I have succeeded with my synthesis or not? And of course, this poses big issues, right? Because first of all, we need to have a lot of microscopy time to characterize many samples, to visualize many samples. But most important, these many samples need to be analyzed. Somebody has to analyze this. And typically this is done by the microscopist. And if you now analyze one image as an expert microscopist in a manual fashion, each image takes half an hour of analysis. And actually there is even a human bias. That means depending on the eyes that analyze this image, some could say a single atom where someone doesn't see a single atom or sees a cluster instead. And this is a kind of image that shows, okay, what do we see here? One single atom, one single atom. Is this a single atom? Yes or no? Is this a single atom? Yes or no? It depends on the microscopist and the expertise of the microscopist. So what we have been doing in this direction to accelerate and, most important, automatize characterization of single atom catalyst is using algorithms to based on automated image analysis for single atom detection in this kind of materials. And what you can see here is the same image as you see on the left with annotations of single atoms according to the neural network. This is a convolutional neural network which detects single atoms on the basis of probability maps. So what you can see is the probability map of the single atom. You can see here the bright spots indicating single atoms, and the algorithm, what we call SAC-CNN, which is freely available in GitHub. You just need to upload your microscopy image and you will get the analysis done in less than 1 second per image, compared to 30 minutes if you do it manually. Gives you, after huge training that we did for the algorithm, the detection of these single atoms. So this is a tool that also contributes to further standardization. Now, I told you before about ultra high density single atoms. So this is a 23% weight platinum on nitrogen doped carbon. And you can see here the bright spots in the microscopy image, right? Now, the algorithm nowadays, in 1 second or in less than a second, will position, according to the understanding of the algorithm, where the single atoms are located, what's the distribution, and so on. You can see here that by yellow crosses. Now, the issue is that if you analyze a little bit more carefully, you will like to know, do I have any clusters in this sample? It's actually quite fair to say that perhaps there are some clusters because, you know, there is a huge metal content, right? Now, our algorithm is able to detect clusters. And let me show you how we do this. The crosses that you see now with circles are actually clusters in the material. The rest are single atoms. So about 10% of this sample is clustered, 90% single atoms. And how do we know that these are clusters? Well, we know that these are clusters or single atoms because of the following. This is 2 single atoms, and this is what we call a dimer. And we know that this is a dimer because the distance between the 2 dimers is lower than the platinum-platinum bond distance. And that means they must be forming a dimer. And this is actually a trimer. What you see over here, this is a trimer. Again, the distance between this and this platinum atom is smaller than the platinum bond distance. That means now that the algorithm is smart enough not only to detect metal species, but also tell you what's your degree of clustering in the sample, which in a way reflects how successful your synthesis was of single atom catalyst. Okay, so all automated, all available, freely available, openly available in the literature. Okay, these catalysts that I'm showing you here, and many of the catalysts I have discussed, are based on nitrogen-doped carbon. And the problem with carbons in general for making single atom catalysts is that they are really nice because they offer you the possibility with high surface areas and many defects to coordinate a large amount of single atoms. But actually, something is a little bit less nice about carbons, and this is that they are amorphous. And if they are amorphous, actually, you don't know the location and the structure of your single atoms and the coordination environment. So the very last part of my presentation actually postulates that the right direction in order to improve the design of single atom catalyst will be to move from amorphous host to crystalline host, so that we could understand better the positioning of the single atoms, and we can then, upon understanding the location of the single atoms, generate new architectures that have unprecedented reactivity. And we put our attention on polymeric carbon nitride. So these are different forms of carbon nitride-based materials. All of them are crystalline, but we focus the attention on polymeric carbon nitride because of this particular proximity of the binding sites in this early stage polymerized form of graphitic carbon nitride, if you like. And so what this particular architecture led to is that because now we know the location where the carbon is, or where the metal will be, because it's a crystalline host, and we are able to prepare ultra high density catalyst, we could actually saturate all these binding sites. So we could go from a traditional 1 weight %, in this case copper single atom on polymeric carbon nitride, to materials where we saturate all the hydrogen sites that can be saturated to produce materials with 18 weight % of copper on graphitic carbon nitride. And the very unique aspect of this catalyst is that now the copper atoms are still isolated, but they are twins. And actually they are very close to each other, about 4.07 angstrom. And this class of materials, which is actually enabled by two aspects. Number one, our host has a crystalline structure, so we know where we are placing the metal. Two, we are able to produce high density. We are able to increase the metal loading to catalyze this proximity of the metals. This is what we call a geminal atom catalyst. And this is what we call a geminal site. Now, these geminal sites can be visualized. You can see this very beautiful micrograph where you see the pairs of copper sites, copper, 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 is stabilized on the structure of polymeric carbon nitride. And what these pairs of copper could afford is actually doing reactions that will be completely impossible to do if these copper atoms will be completely isolated. That means a classical single atom catalyst, where there will be no neighboring copper side, just one copper atom completely isolated compared to these twins, these pairs of copper sides. These copper sides in pair form, as I said, they generate unique reactivity. And they generate unique reactivity because they are quite dynamic. It's not only that they are closed, but they're also quite dynamic. So what I'm going to show you is exactly how dynamic they are. That means that they can shuttle from one nitrogen to the other and get closer than 4.07 angstroms, that's the ground state distance, when you are doing chemical reactions. The driving force of chemical reactions actually makes this transformation from being 4.07 to being closer together. And these findings were published in Nature last year. And I would like to show you what kind of reactions we did to do this, or to visualize, or to witness this dynamic nature. And so what these geminal atoms allow actually is to do very complex organic synthesis possible. This organic synthesis, this is a cross-coupling families of reactions, which will be completely not happening if the copper atom will be only just one isolated. They run very efficiently in geminal atom form, because upon a coordination of the reactants on the neighboring copper sides, and again, the resting distance is the ground state distance, stable distance is about 4 angstrom. Actually, the shuttle mechanism leads them to being only 2.46 apart. And when they are 2.43 apart, these two moieties could couple and then produce the product. When the product desorbs, the copper atoms come back into the ground state. You might not believe this yet because it's a cartoon, but I would like to show you this experimentally. And this is operando electron paramagnetic resonance spectra upon reaction upon a cross-coupling reaction. At time 0, before the reaction had started, we have the ground state of the copper atoms. And these copper atoms are actually copper 1 atoms. Copper 1 is silent in EPR, and that's why we don't get any signal. Now you put the reactants that you want to couple. And so what happens when you put the reactants actually is that a copper 2 signal starts to appear. And the copper 2 signal is actually the oxidation state of copper when it shuttles from this nitrogen atom to this nitrogen atom, and this nitrogen atom to this nitrogen atom. And this is a 2.46 angstrom distance. You can see the development of a copper 2 signal, which is active in EPR, after 5 hours of reaction time in the cross-coupling. Of course, the reactants will be consumed. We are doing this in a batch reactor. And so when all the reactants are consumed after 9 hours, the ground state copper goes again from the purple configuration to the orange configuration, thereby minimizing and eventually banishing the copper signal in EPR, because it goes back to copper 1. Now, these catalytic materials, these catalytic entities have successfully catalyzed extremely complex organic syntheses that are also very relevant for making pharmaceuticals. And this is an example of beautiful chemistry, very complex chemistry, that so far was only available to homogeneous catalysts, that now we can do in heterogeneous fashion because we have atomic level control of the geminal atom catalyst. So this promises multiple applications of solid catalyst in areas like fine chemicals and pharmaceuticals, which before could not be accomplished because of the lack of control in the synthesis of the single atom catalyst. These are high added value products in all cases, as you can imagine. Now, what's the influence of this in sustainability? Why do we want to change from a homogeneous catalyst to a geminal atom catalyst? Well, the answer is here. What I call here E-wins, these are the environmental wins, the gain, environmental gain of using a geminal atom catalyst. And you can see here the process using this is a Sankey diagram of the process for going from reactants and electricity all the way to the product 23 in this particular example, using a geminal atom catalyst versus a homogeneous catalyst. This is what is being used today in industry to do cross couplings. And what you see is that the global warming potential is significantly reduced from 70.3 when we use the standard technology, homogeneous, to the geminal atom catalyst by 1 order of magnitude. It's important, right? And you see here the 5.6 and here 70.3. And now what you can see in this Sankey diagram is what creates this huge footprint of homogeneous systems. Well, you could just see the thickness of these lines, right? And this leads you to here. That's the thickest line in the production of the cross-coupling product using a homogeneous system. Where the biggest burden is in the production of the ligand for the homogeneous catalyst. In our case, with geminal atom catalyst, we don't have that burden because our ligand is actually polymeric carbon nitride. Our ligand is a solid that is extremely cheap. And that's why we can produce not only amazing reactivity, but also, in my opinion, excellent benefits for the environment, shifting from homogeneous catalyst to geminal atom solid catalyst. These benefits for the environment are not only in the carbon footprint of the product, but in many other indicators that are commonly used in life cycle analysis, like the ecosystem's quality. We also decrease the impact 1 order of magnitude. Human health, we decrease the impact of the technology by 1 order of magnitude, and as well as in the use of natural resources. So processes catalyzed by geminal atom catalysts respect the environment much more. In this example, because it's copper based catalysis, most of the burden, as I have shown, is on the ligand of the homogeneous system. If you now go into noble metal catalysis, noble metal catalyzed processes, the biggest burden will be always on the metal. And that's because noble metals have a huge footprint. To produce 1 kilo of platinum, we emit 81,000 kilos of CO2. And that's why having easy to recover catalysts like solid heterogeneous catalyst, and more particularly atomically dispersed heterogeneous catalyst, delivers huge benefits compared to homogeneously catalyzed processes, which are used today for producing fine chemicals and pharmaceuticals. I would like to end my presentation with a video, which doesn't have sound, but it has an image. This is a video of NCCR catalysis. This is the home of sustainable chemistry in Switzerland. I have the pleasure to be the director of this center. I invite you all to visit this website, nccr-catalysis.ch, where we integrate all aspects of sustainable chemistry and catalysis. Not only small molecule activation, but also functionalization of complex molecules and materials, tools for analyzing materials where we focus strongly on operandum methods to follow the dynamics and evolution of catalytic materials and the corresponding mechanistic footprints, digitalization using data science to standardize and to accelerate discovery, and finally, assessing of sustainability. So taking a look into the planetary consequences of developing new catalytic technologies. The video you have seen is our community, our vibrant community in Switzerland. We are about 300 people and 50 groups in the whole country working in all these areas of the process from atom to planet. And I would like, of course, also to finish thanking the people that have done the work that I have presented to you today. And this is my wonderful group. You have seen this, you can see this picture was taken just before Christmas last year. So it's a very recent image. And I would like to thank also especially many funding agencies, right? And not only public agencies, but also companies. My research is application oriented. So I have great joy working with many industrial partners, as you can see here in the bottom line of this slide, in order to implement fundamental concepts into practice. And because I'm giving this lecture to mostly to a Chinese audience, I would just like to highlight an amazing interaction that I have for now several years with NHU, a chemical company in Zhejiang province in China. And, working with them to solve real problems that mostly have to do not only with efficiency of catalytic technologies and reaction, but also with sustainability has been an amazing gift. And so I'm very happy to work with all of them, and in particular with NHU. This is an image taken in Zhejiang province when we were visiting a chemical plant, a very new chemical plant back in 2023. And so it's amazing to have interaction with industry, with very capable people that are trying to do innovations to improve industrial operations within chemical production using more efficient catalysts. It's very important for us in academia to collaborate with industry. And to illustrate that, I have this slide. We need to have a wonderful and efficient equilibrium between academia and industry, because in academia, we are wonderful swimmers. We are able to discover technologies and go through new tools, new reactivities, new materials, new synthesis methods. But ultimately, catalysis was born to be applied, grew up to be applied, and will continue being applied. So it's very important to have the interaction with industry, those that I call divers, in order to really solve real problems and find treasures. And that's why it's very important to have a philosophy where swimmers, academics, and divers, industrialists work together and exchange ideas and information in order to catalyze the development of technologies. With this slide, I would like to finish my presentation. I would like to thank again SmartMat and Tianjin University for the opportunity, and I will be happy to entertain questions. Thank you very much.
Hi, Professor Paris Ramirez. Thank you very much for your very, very wonderful talk. So beautiful, so nice. Yeah. So I think it's including so many figurative, the video, pictures, so can better help the audience understand the process, like especially for catalytic process. Thank you very much. So I also checked the number of the audience. At least more than 2,000 people are listening to your talk on different live platforms. So also our staff will collect several questions from the Bilibili and other live platforms. I will ask questions on behalf of the audiences. For those in person or Zoom, you can directly communicate with Professor Paris Ramirez. Okay, thank you. So also, I have one question. I will ask first. I'm very interested in your work. Yeah, very beautiful, very interesting. Just like you mentioned for the geminal copper atom catalysis. For this structure, during the reaction, the kinetic process, the configuration, the coordination environment just change. The distance will be shortened during the process. Very interesting, this process, to monitor this process. You mentioned the EPR or ESR to confirm this process. Yeah, the evolution for this process, environmental change. So I think just EPR, I think for this test, just confirm the formation of the appearance, formation of the defects, actually. The coordination, maybe environmental change. But I think, I don't know. Yeah, I just wonder. So is suitable, is it possible to do the X-ray absorption spectroscopy, for example, EXAFS, for this, this characterization to further confirm this process? Because I cannot just, I don't see the picture. Okay, thank you. Very interesting work. Yeah. For this.
Thank you. Thank you, Chichen. No, I think it's very challenging to follow this by exafs. I think we haven't tried to do this for this reaction in particular, but we are trying to do gas phase reactions using geminal atom catalyst. And I think the problem with EPR with exafs, it's always the fact that it will only work if we are able to make very uniform sites. And in this case, we have a large majority of uniform sites, but we know that there are some copper atoms in these materials that are fully isolated, that they are not in pairs. So I think that, let's say the use of average techniques like exafs will only be, let's say, highly beneficial for this once we are able to synthesize fully geminal atom catalyst. And that's why, as long as we have heterogeneity in the solid, then it's very difficult to assess fully with exafs the dynamics of this. You can get hints, but it will not be as quantitative as in this particular case, EPR.
Okay, thank you for your reply. So also our staff have collected some questions from the audience in different live platforms. So I will ask a question on behalf of the audience. One question from the audience. What about, especially for thermal catalysis, what about the stability of single atom catalysis after the reaction, especially for the high metal content single atom catalyst? Thank you.
Yeah, very good question. It's something that one has to take into account. For gas phase chemistry, if you, for example, the example I've shown on acetylene hydrochlorination, the catalyst is extremely stable even at high loadings. But indeed, this is acetylene hydrochlorination is probably 170 degrees Celsius. So for much higher temperatures, one will have to have precautions. I think that, again, it's very difficult to exclude that some of these metal atoms will cluster. But I think that the notion that the person making the question have to keep in mind is that if we are able to design the right binding site, then we can control the metal host interaction to keep it stable under a certain reaction condition. So I think every case is different, but I think we have the tools to control the metal host interaction to make them stable even at under harsh conditions.
Thank you for the detailed response. Another question, Chinese. Okay, I have to translate. I think the meaning is for the audience. What's the mechanism for CC company? Just now you mentioned for C3 to C6 products for CO2 electron reduction. For that, yes. Now C3 very challenging for this process this product. So how to improve the selectivity towards C3 to C6 products in CO2R test? I think the meaning like this.
It's a very good question, also very difficult question. But the mechanism is more or less clear. The mechanism is very similar to Fischer-Tropsch synthesis. So it's basically CO cleavage and carbon insertion in the hydrocarbon change. So the CO2 to long change hydrocarbons, it's a way to do Fischer-Tropsch at ambient temperature, at ambient pressure, using CO2 and using water instead of syngas. Now, that's as for the mechanism. And we know that because we have very typical so-called ASF distributions, Anderson-Schutz-Flory distributions, which are reflecting a Fischer-Tropsch mechanism. Now, that's as for the mechanism. Now, the other very important question that the audience asks is how we can improve the selectivity to C3, C6, etc., right? And this is where we are working very, very, very actively because, the reason why we have limited selectivity still, so the Faraday efficiency is not higher than 15% so far, is because there are parts of the nickel catalyst that are reduced. And this fully reduced nickel will actually render hydrogen. And that's why we lose the Faraday efficiency into reducing water rather than reducing the carbon dioxide. So the approach, I think, will be to be able to keep this polarized nature of the nickel all over the surface of the electrocatalyst. And that is very challenging because, CO2 reduction are reductive conditions. So naturally, you will need to find some tricks, probably playing with additives, not only in the solid, but also in the electrolyte, to keep the surface of the nickel side polarized. That is not to lose all the oxygen that you put in during the synthesis, and that is extremely challenging. So I don't yet have a better answer than this.
Thank you. Yeah. So any other questions for the professors and the students here? Yeah.
Hi, Javi, I'm Zhupen. So it's very nice to hear your talk again. So hello, Professor Zhichen Tang. So I have a few questions to ask. So first, I also want to follow the question from Zhichen. The question about this copper geminal atom catalyst. So I have two questions in this study. The first question about this will be, could the method used for the production of other geminal catalysts based on other metals, so for example, the nickel, iron, anything else?
Thank you, Zupeng. Yeah, obviously, we have started and we have already some good results on geminal atom catalysts that are not only based on copper, but all other metals. We have indeed created iron geminal atom catalyst. We have created nickel geminal atom catalyst. And the most important is that we have also created bimetallic geminal atom catalyst, because you could imagine that it would be very nice to have pairs of different metals in proximity to do some tandem chemistry or some particular reactions that will require metals of different nature. So this is all possible. I think for monometallic geminal atom catalysts, we have been able to see it, as I said, for iron and for nickel. We're trying to find good applications of these materials. So that's on that side. I think that nothing precludes nothing precludes to do this for noble metal catalysts. So I think it can be done. One would need just to set an application and develop it. And another comment I have for the bimetallic systems, and I think that would be a challenge in the near future, which I think we, as well as many others, will start working, which is what kind of characterization method we develop to know exactly what is the statistical proximity between different metals. If I have, for example, copper and nickel in the catalyst, what's the fraction of copper and nickel that are in close proximity? It's just copper sides, which tend to be together, or nickel sides, or copper-nickel sides. What is the distribution of the three different possibilities? And that is a huge characterization challenge, because you will need to have a spatially resolved method to detect which metal is close to which metal. And you can imagine for metals that have very similar kind of imagined contrast in microscopy, that would not be possible to distinguish or to differentiate. And so that's a challenge, how to characterize multimetallic geminal atom catalysts. That's something what we are working, but I think it's very nice if we, as well as the community, finds other applications of geminal atom catalysts which are not only based on copper. But, this is a very new result. It was only published, I think it was published somewhere in September or October. And so I think this is prompting a lot the community to identify new reactions and new metals, Zhupen.
Yes, actually, this bimetallic system will be quite difficult to characterize. Yes. For this system, I have the second question is that how the performance of this standard copper single atoms, if it also works for the same reaction or not? If it's not,
beautiful. Yeah, the reaction, the activity of let's say conventional single atom copper catalyst for all these cross couplings is zero. They don't work at all. You need to have these pairs. You need to have these pairs of copper. This is what makes it very important, right? Because by increasing the metal loading, we were able to increase metal proximity. And by increasing metal proximity, we have discovered an application, in this case, cross-coupling, that actually could not happen with the standard single atom catalyst.
Okay, because my the follow-up question is that how it is possible to increase the density of copper atoms so that they may resemble the geminal catalyst, but apparently it is not possible. This is really very strange. Because
I think in principle you need to have this very, very particular geometry where these copper atoms are very close together. But these are single atoms. These are not dimers.
Yeah.
And they are not electronically coupled. That's why we call them geminal atom catalysts and not copper dimers. So that's very much influenced by the structure of the carrier.
Mm-hmm. Okay. Wow. This is still a lot to explore.
a lot to explore. I agree. And that's why I put this image where they have these pictures of the man and the woman together, right?
Yeah.
It's the single atom catalysis or geminal atom catalysis is not only to think about the metal. Actually, you have to think more carefully about the carrier than about the metal.
Okay. Yeah. Thanks, Javier. Yeah.
Thanks to you.
Okay, thank you. So any other questions? Professor
yeah,
okay.
Very nice talk, Professor Ramirez. And it's very interesting that I say that you show that the distance between the two copper atoms in the geminal catalysis, that is very important in the catalysis. So my question is that whether the distance between the dimers of the coppers, different dimers, dimer to dimer distance also play as those in the catalysis.
Yes. Yes, that should certainly play a very important role. But I think at the moment we are not able to control that.
Oh.
So we are not able to control that synthetically. And I think we don't have yet a mean to understand what will be the situation during reaction conditions. So I think that comes back to the same question of host design. You know, we will need to have an architecture. We will need to have an architecture, and you know, it's very. I mean, obviously, one could develop. One could try to develop copper dimers on carbon-based materials, and probably one will get an amazing performance. But then we hit back into the issue of not being able to characterize properly carbon-based materials because they are amorphous. So I think this crystallinity aspect in the host design is something that one has to keep in mind very seriously.
Yeah, exactly. And and I have another question. Can you hear me? I have another question about the characterization techniques. And you see that you show that especially the geminal catalysis, they are dynamic in the reaction. So my question is that whether it is also dynamic under the TM technique, I mean the environment, like you shed the electron beam on the catalysis, that will that cause the changes in the configurations or not?
So absolutely. And yeah, this is a big challenge. You know, I show you this image of the geminal atom catalyst, you know, by microscopy. That image took a long time to record, because most of the time the electron beam will actually create a dynamic change in the catalytic material, right? So this was not a one-shot image. This is a very difficult to acquire image. And so I think the challenging characterization microscopically of this geminal atom catalyst is very high. It's a very challenging.
Oh, okay. Thank you.
Welcome.
Thank you. Okay, thank you. So any other questions?
If no more, I can have a few more. Okay, so another question will be the two-step annealing method, because I also tried this method actually. I sometimes I find the difficulties where to try to remove the excess metals, because when I do, I think I did quite a lot of washing step, but anyhow after the annealing, the second step annealing, I still have quite a lot of particles. So it's a little bit strange how it's difficult, actually just difficult to remove all of the excess metals.
Probably you could improve your synthesis skills, Supen, because we have been able in some cases to remove this metal, and sometimes it is fair to say that probably you need to work in non-aqueous media to remove the excess metal.
Yes. Okay.
So I think it's also it depends on the is your host, what is the properties of your host? This will also be quite relevant, right?
Yeah.
And again, it comes to the standardization aspect.
Yes.
If we will all be using the same carrier, then probably I will tell you, okay, it's strange that you don't reproduce my results. Something is going on, but your carrier is very different to mine. I'm pretty sure.
Yeah.
And that's what the next. I think that, in my opinion, that's where next effort should be concentrated in catalysis. We need to use materials that are so well reported and so well standardized that there is no doubt of interpretation of how to make this material so that we all get a reproducible sample.
Yeah.
You agree, Supen?
Yes. Okay. Then another question will be in this CO2 electron reduction, I think with nickel nickel catalyst, right? You have a small when you change, because normally the nickel catalyst, the metal part, right? The standard nickel catalyst, it's not so good for CO2 reduction properly. And you change a little bit the nickel zero to nickel two plus, right? The positive charge. So how this small amount of this positively charged nickel change this kind of reaction pathways of this CO2 reduction?
Okay, I think I mentioned that during my talk, but probably I did it very fast. What happens is that if you just polarize nickel, then the binding energy of CO decreases substantially. And so in metallic nickel, the binding energy of CO, that means upon removing one oxygen from CO2, right, is very strong on metallic nickel. And what happens is that you poison the catalyst surface of nickel. That means that carbon moiety cannot desorb. And instead of reducing the carbon dioxide, you will reduce the water into hydrogen. If you introduce this oxygen, if you dope the nickel by oxygen, producing polarized sides, the binding strength of CO gets weaker. And that enables the products to evolve. Now, there is another step, because that will evolve as CO. But instead of CO, we make multi-carbon products. And that is because also upon polarizing the nickel, you decrease the barrier for carbon-carbon coupling.
Mm-hmm.
Yeah. So the oxygen leads to two effects: lower absorption energy strength of CO and lower barrier for coupling carbon moieties on the catalyst surface.
Mm-hmm. Okay, yeah, thanks, Jaime.
And on this topic, Tsupen, more needs to be explored. I think more studies need to be done, because this was the first ever study where people will use something that is not copper.
Yeah.
To oxidize, so to reduce carbon dioxide into hydrocarbons.
Yes.
And
okay.
you can imagine that other metals that have been used in thermal catalysis very frequently, like cobalt or iron, right? The typical Fischer-Tropsch catalyst. In electrocatalytic way, they could also find a way to produce multi-carbon products from CO2.
Mm-hmm.
So I think nickel will not be the exception. We will hear soon alternative metals that could even make longer hydrocarbons than nickel.
Mm-hmm. Yes. Okay, good.
Yes, very good idea.
Thank you.
In CO2 electron reduction, actually now currently cascade tandem catalysis also is a very effective strategy to improve the CC coupling. But not sure for C3 or C6 for these products. And not sure this is effective strategy or not. But for nickel, yes, polarized nickel can try.
Yes.
Okay, thanks.
Yes.
Also, our staff collected one question from the audience. Is it possible to construct all the oxygen vacancies? Yeah, just now you mentioned for thermal catalysis, I think from CO2 to methanol, for that work, oxygen vacancy very important. So what about all the oxygen vacancy for indium oxide or tin oxide like this? I think his meaning or her meaning. Yeah.
It's a very good question. And yes, this can be done, but you need the reason why indium oxide has been so successful. I think I saw a few days ago this paper in Angewandte where we reported indium oxide for the first time. I think the paper probably in 2016, this paper has close to 1,000 citations. So it's very unique. It's very unique architecture. And the reason why it works is because indium oxide is an anisotropic oxide. That means you have different types of oxygen sites with different energy for vacancy formation. That means there are some oxygens that are easier to remove than others. At least on the surface of indium oxide, there are 7 crystallographically different oxygen sites. And that allows to remove one or other depending on the conditions, the reducing atmosphere. You can reduce some of them, keeping the others in the structure because they are stable at this condition. And that allows to form ordered vacancies. And for that, you need the anisotropic oxide. Other oxides where you could form vacancies, for instance, cerium oxide is a very, very nice material for forming vacancies, right? To improve, oxygen transfer and so on. But it's much more difficult to form, or even impossible, or not possible today, to form ordered vacancies on this because they are isotropic. That means that at a certain condition where you form a vacancy, all oxygens have the same quality. So it's very difficult to control a specific sites where a certain vacancy is isolated. So my advice is, if you want to control vacancy formation, you need to work with anisotropic oxides in order to achieve some success and control.
Okay, thank you, Professor Paris and Ramirez. Yeah, very long time now, 1 hour and 40 minutes for your talk.
That's very, very good. That's very good.
Yeah. Still, I think there's so many questions for the audience. So if you have any questions, you can send an email to Professor Paris Ramirez. Okay.
Yes, please do so.
Please. Thank you very much. Thanks again for your wonderful talk and the detailed response to all questions from the audience. And here also. And also welcome to visit the channel, Tianjin University, and welcome to submit your work to SmartMat. Thank you. Thanks for your strong support.
Thank you very much. Thank you very much for the invitation. And wish you good luck with the journal. I think you are doing very well, and I hope to submit some work to a SmartMat soon.
Okay, thank you. Welcome. Okay, bye.
Thank you so much.
Bye-bye.
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 Thank you, everyone.
Bye.
Have a wonderful evening. Bye-bye.
Bye-bye.